Wait, you went from Perez tries.
I did this and I turned this
So you still need to parameterize, or can you just go straight forward? I guess.
I think we still need to parameter, like I guess. Maybe we're gonna
Did you?
I parameterized and showed well, I guess like that's partial. Oh. No, we didn't parameterize, they did it for us, that's why. Okay. So then we have to convert it to something else. So yeah, at this point, I think you see that, I mean, I'm sure you could do the physical, just I don't want to. So then you convert to over, some portion of the circle.
So I would just say, it would just be like S squared plus T squared equals 1. Yeah, that would
Pulling down. I can't figure out how to do that.
Wait, can I try to like record it? Wait, one side.
I always twist it this way and then this side.
Oh, it's blue.
Yeah.
Switch them to my source. Oh, I'm twisting the wrong way. It's the right way. I was like a little tough. Yeah, because that feels that doesn't look like it's the same way. All right, so when I sub in, do I leave these limits of integration? Well, no. But then how do I change the limits? I just come up with new limits. So it would be 0 to 2 pi.
So I was just top of all this one.
I didn't know. I took my AP sequence and then didn't do it from like 7. Yeah, but then I took nothing from 7 to like 1. Nice.
Okay, so believe it or not, it's actually time to get started. And I understand that there's an issue with the buses and that people will be coming in frantically a little bit late. And for those who come in late and are probably now listening on the recording, no problem. Don't worry about it. We'll do attendance when class is over and no issue. Okay, so quick reminder though, what we were doing last time, we were talking about Stokes' theorem, and we'd actually done quite a bit, but we got a significant amount more to do. So very first thing we had to do is we had to define the convention for what we mean by the orientation of the boundary, right? And so whenever you talk about boundaries in this class, in this part of the class, that is, boundary means something specific about the orientation of that, you know, the edge in whatever sense of whatever kind of object we're talking about. So this is the convention here, described like so. And again, arbitrary, but standard. And so not optional. Okay, next thing to observe. There is this accumulating quantity. This is a lot like with Green's theorem. Boundary circulation is the accumulating quantity, and why it's an accumulating quantity is a very familiar picture. And it's a very familiar argument even, that it's like this edge appears twice with opposite orientations as the part of the boundaries of the pieces on each side, and they cancel. And so just like with Green's theorem. In fact, I think this is kind of funny. If you were to draw on a piece of paper an argument for why boundary circulation accumulates in the two-dimensional context, if you were then pick that piece of paper up and do like this, well, now you have a three-dimensional model of why Stokes's theorem works, right? Or why boundary circulation accumulates in 3 dimensions, which ultimately is why Stokes's theorem works. So it's really the same argument. Okay. Then we have this associated notion of density. So again, whenever you have an accumulating quantity, that means that the stuff that you're measuring, even if you feel like you're measuring it on the boundary, right? If it's an accumulating quantity, it is literally accumulating throughout the interior. And you can talk about there being some of it in specific places. And there is therefore this associated notion of density. And density in this case, circulation per unit area. And it's something that can be computed. So as we discussed last time, circulation density computed by this formula. It's curl.n. And I promised that we would later come back and talk about this .n business. And that later is a couple of minutes from now. Anyway, well, let's not get ahead of ourselves. Okay, so putting all this stuff together, I guess I'll go ahead and zoom in. I might as well zoom all the way in here. Putting all this together, okay, so we're looking at circulation. We have this concept of circulation. We argue that circulation is an accumulating quantity. That allows us to take this step right here. We're looking at a total. It is therefore the sum of its little pieces. And then being an accumulating quantity, we can talk about how much of that accumulating quantity there is per unit area, thus giving us the associated idea of a density. And having written all this down, right, having put these Lego pieces together in exactly the same way as we've done several other times, and then recognizing, just for if only for notational convenience, that we can rewrite that as such, then we have ourselves a new theorem, and this is Stokes's curl theorem. Okay, so this is almost where we left off last time, but I just wanted to hit those highlights again. Yeah.
Just a quick question. So
Yeah.
how is Stokes's curl theorem different from just applying Green's theorem in 3 dimensions?
Because there is no such thing as Green's theorem in 3 dimensions. Green's theorem is very, that's in some sense, it's a terminological complaint here, right? But Green's theorem is very specifically about 2 dimensions. But yeah, a lot of people like to think about Stokes's curl theorem as being kind of a 3-dimensional version of Green's theorem. Absolutely. And certainly, I think Green's theorem is a great thing to have done before doing Stokes's theorem, because the analogies are really very helpful. Yeah.
Yeah, because I think in the last homework there were problems where we had to determine if there was an anti.
Yeah. Now that's different. So that argument there is not, well, the proof of the tool that you're using there uses Green's theorem, and likewise the proof of the tool that you're using there in 3 dimensions uses Stokes's theorem. But we hadn't presented that proof at that time.
Right.
So really, those are just yeah. Those, think of those. Those are related but not identical properties of these operators. Yeah. And in fact, we're going to close that loop, no pun intended, in a couple of minutes here. We are actually going to that issue that you're talking about. We are going to prove that with Stokes's theorem today. Yeah, assuming my plan goes according to the plan. We'll see if that bears out. All right. Okay, so we did this example, and the big upshot is if you have a curve that is a boundary, which we do here, that curve is the boundary of this region oriented thusly, right? then great, you're looking at a boundary circulation. Well, boundary circulation can be computed with Stokes's theorem. And then it's just, so we've transformed the question, one question that was looking really hard, right? We transformed that now by using Stokes's theorem into a totally different question, but which happens to look really easy. And I just noticed I have a typo in here. I don't know how I managed to miss that, but this needs, of course, to be DS there. Sorry about that. I will get that fixed. So hard problem turns into an easy problem, as is surprisingly often the case when you use these accumulation theorems, the divergence theorem, Stokes's theorem, fundamental theorem of line integrals, Green's theorem, etc. Okay. All right. Okay, that's where we left off, I believe, last time. Okay, so let's go back now and talk about what's the deal with, let me go back to it real quick. What's the deal with this dot in that we see right here? So there's something a little weird about it. If I've got a vector field that about which I want to talk about circulation density in general, if I have some function of any description and I want to talk about some associated density, whatever that is, right? You would think that the density of the thing only depends on the thing, right? And so that's what's kind of not happening here. That's what's weird. I've got this vector field, and about this vector field, I would like to know its circulation density. And the answer says, well, I don't know, it depends on you. Which way are you oriented? Your little piece of surface, right? There's something awkward about that. So what I want to start with is to point out that this is actually a situation we've seen before. And I kind of addressed it quickly because I knew I was going to be coming back to do it again for exactly this reason now. So now I want to give this a little bit more thorough of a treatment. But we saw this when we were talking about the fundamental theorem of line integrals, right? And here's the what you might call the first version that you write down of the fundamental theorem of line integrals, because if you want to talk about the density that allows you to compute change from size, well, here's change, here's size. Size is ds. And so your associated density unavoidably is, check it out, gradient dot t. And that t depends on the curve, not just the function, right? So we've got the same situation here. Hey, how fast is this function changing? What's the change density of this function? Which way are you pointing? Right? It seems weird, right? The function itself is what I want to talk about. How much is it changing? And which direction I'm looking, I mean, I see that it matters, but it just kind of feels like it shouldn't, right? So the way that we address that, the way I like to address this, is to notice that if I do take advantage of our old fact that this t, that's part of my density, if I combine that instead with my ds and write this as, we have previously as dx, notice we get something that really does only depend on the on f. We get this thing, the gradient of f. Now, is this a density? In the traditional sense, no. This is not something you multiply by scalar size to get scalar change, but this is a really similar thing. This is something that I don't multiply, but I dot. Dotting is kind of like multiplying. I dot it with not size, but what you might call oriented size, right? That's what the dx vector is. It indicates the size, but it also indicates the orientation. So this is something that I'm going to say this sloppily for persuasive purposes. I oriented multiply by oriented size to get change. This is kind of, in an oriented context, it just sort of makes sense that I have an oriented density that I oriented multiply by an oriented size instead of in our more familiar situation, erase. In my more familiar situation, I like to think of densities as a scalar thing that I scalar multiply by a scalar size to get my quantity. So anyway, arguably this is just a rewrite. Arguably this is what you get by, when you group these, and this is what's left over. But I think it makes great sense to think about this as an oriented density. Right? And beautifully, this furthermore is something that answers a lot of questions for us. This is something, for one thing, it is intrinsic to the function. This gradient does not care which direction I happen to be walking or which direction I happen to be pointing. It's never heard of me, right? This function is what it is, independent by itself. And this thing I'm calling the oriented density, the magnitude of it is telling you something pretty natural. The magnitude is telling you how steep the hill is, right? How fast the function's changing in the direction that, of course, it's actually changing. And if I go off in the wrong way, then of course, I'm not going to experience as much change as the function's doing if I'm not going the right way, right? But in a very natural sense, this is telling you how much the function's really changing. And then furthermore, it is also telling you by way of its orientation, what that direction is in which the function is actually changing. Okay, so this is this concept of an oriented density. Again, it algebraically, it just kind of falls in your lap as a result of this kind of compactifying little rewrite, but it really makes a lot of sense in a lot of ways. Okay, now with this as background, I claim morally the exact same thing happens with Stokes' theorem. So again, now here's our first version of Stokes' theorem, right? And this is density, as we've discussed. This is what you multiply by area to get circulation on each little piece. So that's my circulation density. Okay, but let's do the same rewrite. Let's combine these together as we already have. This familiar notion of this ds thing. And now let's try to make sense out of what this guy is. This curl F that sort of is left over. Well, for one thing, it's intrinsic to the vector field. It does not care about which way my piece of surface is oriented. This is about the vector field and only the vector field. And so it makes sense to call this, a feature of something intrinsic to the vector field. Just like up here, the gradient is intrinsic to the function. Furthermore, it's, I'm not scalar multiplying by size, but I am oriented multiplying by oriented size. Again, think about what this ds vector means, right? This goes back to 7.2, but this vector is telling you both the orientation and the size of that little piece of surface. So so this is an oriented thing that we oriented multiply by oriented size to get circulation, compared against this, which is a scalar thing that we scalar multiplied by scalar size to get circulation. So it's just, I think it's reasonable that everything that's happening here is an oriented version of what's happening above. And I think it makes sense then to call this oriented density, oriented circulation density in this case. So anyway, I think it's a nice point of view. Again, just like up here, where even though I've kind of motivated this algebraically, but it also breaks down into geometrically natural sort of, parts. The magnitude and the direction of the gradient both mean something natural. And likewise here, the curl has a magnitude that tells you ultimately how much is this vector field rotating? How much of a tornado have we got here? The magnitude of the curl is what tells you that. In the same sense as up here, it's the magnitude of the gradient that tells you how much is the function really changing, right? And likewise, the direction of the curl is telling you in what direction is this circulation happening, more specifically, in what around which direction, right? So what is the axis? What's the direction of the axis? Around which direction is the circulation happening? In the same sense that here, this vector is telling you in what direction is the function actually increasing. So the analogy is quite strong. And I think this is a really useful way, again, to think about curl. We recover, with an asterisk, we recover our previous sort of pattern that our new integrands are densities. This is just a different kind of density appropriate to the context. Okay. All right. So here's some pictures to illustrate what I'm talking about, and I'm starting off with just a sort of a restatement of what I had on the previous, on the last line of the previous page there. But the curl, having as it does a direction and a magnitude, right? The direction tells you about what is the axis that this fluid is circulating around, and the magnitude tells you, in some sense, how much. And so I don't know how to draw this exactly, but it's telling you, is this a strong tornado? Is this a Cat 5 or a Cat 2, right? Wait, that's hurricanes. But whatever the terminology is for tornadoes, just how much circulation, how much is the fluid spinning around this axis, right? So roughly speaking, this is a picture here of what curl looks like. Curl is pointing in the direction of the axis that you're circulating around, and its magnitude tells you how much. So with this picture in mind, I'm going to come back up here. Let's see, where is it? Back up, I guess, to here, where I made the observation that curl with these features, dot in tells you how much actual circulation density, scalar circulation density you have. And I want to show you some picture examples of how I think that actually tracks pretty well. So here they are. Let's consider these two cases. This vector field and this vector field are the same. So literally copy paste, those are the same vector fields. I just want to draw sort of two scenarios to think about. Also, this circulation, oh, come on, stylus. This circulation that we're seeing here, it continues along down here. I just didn't want my picture to get all sort of cluttered. All right, so in this case here, in this scenario, we've got this vector field, we've got this little piece of area, it's got a boundary that, of course, relates to the direction of the normal vector and all that. So what's going on in this picture? How much circulation do we have? How much circulation is this surface boundary actually experiencing? Well, a lot, because there's the circulation of the vector field itself. The boundary is going around the same way. This vector field is really, no kidding. That vector field is representing a literal circulation around this boundary. And notice that because of the geometry of the situation, this corresponds perfectly to the gradient and the normal vector pointing in kind of the same direction, right? So this dot product being large tracks with the circulation that we would detect on that boundary being large. Okay, now by contrast, let's look at this scenario here. So I'll zoom up a little bit. This is a kind of a disappointing sort of scenario, but here's my vector field. Right, there's a big tornado going around that line. There's a lot of circulation of the fluid itself, but the thing is, this piece of surface here, the boundary of it is boundary of it's going kind of this way. The circulation, I mean, this is a hard sort of coordination problem, but the circulation's going like that, but my boundary's going like this. It's out of sync. They're not doing the same things. And in fact, if you were to take the actual vectors in this vector field and draw what they are doing over here, those vectors, right, are like this. And are they going in the same direction as the curve? No, they're going perpendicularly. So no circulation is happening around this piece of boundary. And again, that tracks though, right? Because if you look at, now let's look at the, what would the dot product pick up? Well, the curl of the vector field is like that. And then the normal, the orientation is like that. And again, the dot product doesn't pick up either, right? So when the circulation is kind of out of phase, out of whack, whatever you want to call it, the circulation around the boundary is out of, whatever you want to call it, it just isn't working in exactly the same cases where the dot product likewise kind of is just, well, they're just in different directions. And I think you can probably use your imagination when I'm going to make the case here that if you were to imagine some scenario sort of in between these, as you know, let's say, okay, here's my curl vector, right? As my piece of surface that's out of that pointed, that's oriented the wrong way, as it starts to sort of bend over toward the correct orientation, that dot product sort of increases continuously between these two extremes in the same way that the circulation likewise sort of increase continually between these extremes. So I think this formula here, yeah, here it is. This formula, sorry, wrong one. This formula, curl dot in, really makes a lot of sense. Now, this isn't proving anything. This is just kind of I'm just intending this as a, intuitive satisfaction. But I think there's a lot of intuitive satisfaction to be had that this actually kind of makes sense. This formula tracks with this interpretation of curl. Okay, that's a lot to digest. Right? So give yourself time. Again, let me remind you, I'm a big believer in the recordings of the lecture here, right? And so if you kind of got a little lost along part of that, well, of course you did. I'm cramming a lot of ideas, very geometric, at you all at once. So watch a repeat of this and give yourself time to digest those ideas. Okay. Let's talk about some physical examples. I don't have as many here for curl as I did for divergence, but I think they're pretty satisfying. So remember, we've talked about Green's operator. And in fact, let me zoom in here. Green's operator, in some sense, is telling us how, if I have here, I'll use orange for the leaf. If I have a leaf floating on the surface of a river, dead leaf, right? As would be likely to fall off a tree. That dead leaf floating along, well, the actual flow itself, keeping in mind that here we're using the velocity as the representative of the flow. The water is telling the leaf exactly what to do. If the water is moving, the leaf's going with it, right? So the leaf's velocity is the same as the water's velocity, which is just the vector field. This is a, off-speed pitch. Don't overthink it, right? The leaf goes with the water. Of course it does, right? But now let's ask the harder question of, well, yeah, but as that leaf goes down the river, does it go kind of like this, right? Or maybe does it kind of twist? Does it kind of turn as it floats down the river? And I don't know if y'all have ever sort of noticed, if you look at a little creek or something or whatever, and the leaves floating down, yeah, they tend to kind of spin around as they go down there. Well, Green's operator is what is telling you how much the water is kind of turning, how much the water has got a little bit of a twist to it, a rotation to it, lots of different ways you could describe it. And that's what controls the leaf's rate of rotation. And I think in this case here, you can kind of see the water is pushing it harder on the bottom side than it is on the top side. This leaf's probably going to be sort of turning counterclockwise. And Green's operator measures that. Okay, in exactly the same way. Now I can't talk about leaves floating down a surface of a river, but I can talk about a three-dimensional version of that. I'm going to talk about a floating balloon. Weighted to be exactly the same weight as the air, so that I'm going to factor gravity out of the situation. Let's ignore gravity, right? So this is perfectly weighted and it's floating. It's got just exactly the right amount of helium in it, and it's nevertheless being moved around by the air. Well, again, not a lot of mass here. What's this balloon going to do? How fast is this balloon going to fly? Well, the balloon is going to do exactly what the air does. So whatever the vector field is, that's telling you the velocity of the air. That's telling you the velocity of the balloon, right? Again, it's, don't overthink it. The balloon does what the air does. Likewise, curl is going to tell you how that balloon will be sort of turning. And oh my gosh, I forget to turn this off. Sorry about that. So curl is going to tell you how that balloon will be spinning or twisting or rotating, or whatever you want to call it, as it goes. Specifically, the axis that the balloon will be twisting around is the direction of the curl vector, and how much. Is it going to be, is it twisting fast or is it twisting kind of slowly? How much is given by the magnitude of the curl vector. So just like Green's operator in 2 dimensions, analogously curl in 3 dimensions. All righty. Okay, so I feel necessary to mention, if only very, very briefly here, something about magnetic fields and currents. This is not a physics class, and there is a lot of physics to be said here, and we're not, again, not our job. We're not going to go off as too much. They have entire courses, right, on electricity and magnetism. So, but what I will say is, just real quick, if you have a flow of charged particles, flow of charged particles it's a flow of a fluid, right? It's a fluid where we're not interested in the mass of it, we're interested in the charge of it. So it's physically a different kind of different aspect of the fluid flow that we're interested in. Nevertheless, we can describe that with a vector field. And I messed this up. This J here, I wrote J after. Previously, I was going to describe it as F, and then I was like, let's go ahead and be physically representative. J is the standard, and then I forgot to change it here in the diagram. So sorry about that. In fact, let me cross that out in red. That'd help. This is J, the vector field of charged particles. J. Okay. So if you have a flow of charged particles, here's just how the world works. By the way, don't ask me why. Why does the physical world work like this? Nobody knows. This is all empirical. This is observation. There is no why, particularly. But what happens is it creates a magnetic field, right? So when you have this flow, let me go back to when you have a flow of charged particles, that creates a magnetic field. And the way magnetic fields work, and again, I think this is weird too, totally, but this is just empirically what happens. The magnetic field goes kind of in sort of, in this simple case of a straight flow of current in a single direction, it makes kind of loops around the current. Okay. All right. And as it turns out, that circulation, So the circulation of the magnetic field that's created by the current, you can see it's going around in loops. It's natural to ask how much is it, what is this, how much of a flow of the magnetic field is there? That circulation is proportional to the amount of current that goes through that loop. So how, however much current is going through the middle inside of that loop, that current gives you the circulation. Again, empirical, right? So having observed that, well, a couple of quick observations. So for one thing, current is literally the flux of the flow field. Current says how many charged particles are moving through your surface. That's literally flux. Flux of the vector field describing the flow, that's J, right? So this is just an observation about what the definition of current is. And then down here, this is literally straight up just Stokes's theorem. Right. And so when you combine those in, just like we saw with the gravity example and the electricity example, we can kind of infer then something about these integrands and specifically the magnetic field that is created by a current. The curl of that magnetic field is proportional to, anyway, the original current field. So the physics of the result here is not the point, right? Again, it's not a physics class. The point here is that we can use Stokes's theorem and the idea of flux. I want to focus more on Stokes's theorem here. We can use Stokes's theorem to draw a connection between two seemingly different physical observations. So, this observation right here about circulation and current on its face does not look exactly like this observation here about flow fields and curls of magnetic fields, but they're morally the same statement. And again, as such, they go by the same name. This is Maxwell's fourth equation. Two different versions, right? This is the integral form. This is the differential form, whatever, but they're morally the same equation. One's a global version, one's a local version. They're immediately connectable by way of Stokes's theorem. So that's the point, the relationship between these facts, not the facts themselves. Okay, everybody with me? All right. Okay, so y'all remember this business with Green's operator, and this is what I called back in chapter 6 a local test, because there is a test that you can apply. Just take Green's operator, see if you get 0 or not. If you get 0, there's an anti-gradient. Your vector field is a gradient of something, and you can find that something that it's called the anti-gradient. Okay. And let me just remind you that the argument was to observe that path independence, being a gradient, being path independent, closed line integrals being 0, these are all the same statement, right? Being path independent, and Green's operator being 0, and again, now there's a little argument to be made here, but if all possible integrals are 0, then the integrand would have to be 0, and I claim that those are pretty believably the same statement. But these concepts are connected by way of Green's theorem, because Green's theorem relates these closed line integrals to these double integrals, right? So Green's theorem is the foot in the door that gives you the local test in R2. And now check it out. You know what? Let me go back to here real quick. Here's my, here we were in 2 dimensions. This is the exact argument that I just went through. And then recall, down here, I gave you, and this is what you were asking me about, I gave you this 3-dimensional version, you use curl, and then I gave you an apology instead of a proof, right? I said, well, we don't really have quite the tools to prove this yet, right? But Stokes's theorem is that theorem, this theorem. And so let me point out how that works. And I'm going to try to fit both of these on the page at the same time. So now in R3, Well, there's still this idea of path independence, right? And now, though, what is it that connects? What can I say about closed line integrals? Well, closed line integrals in R3, it's Stokes's theorem that allows me to connect that. And it's not to double integrals, but to flux integrals. That's what Stokes's theorem says, right? And then again, I can make this observation that, well, look, how could all fluxes, really now, how could all fluxes of some vector field be zero? All of them, no matter what surface, every flux of this vector field, all zero? Well, the vector field's got to be zero. And vice versa. Okay, so notice, same argument. And again, I think this shows up really nicely. I love colors with the so I use consistent colors here. So you notice it's the exact same argument, just in a three-dimensional context instead of two. Stokes's theorem being the linchpin instead of Green's theorem. But that's what gives us now our three-dimensional local test, that curl plays the role of Green's operator. Curl is the thing that gives away whether there's an anti-gradient when you're in three dimensions. Is that cool? Okay. Yeah. All right. Okay. So here's a new idea. This is a very underappreciated idea in my own personal opinion. Our textbook's treatment of this idea is, I kind of feel like they hit all around it, but don't ever really quite say it. They give an argument on this that every time you use it requires significant setup and worry about, but the orientations and the this way and the that way, and their version of it is confusing to implement. And I'm going to give you a version that once you see how this, once you see the setup, it's much easier to apply. So the new idea is going to be called surface independence, and as you might guess, it is a kind of an extension of the idea of path independence. So I'm sure y'all remember path independence. Let me just remind you for setting up analogy purposes. If you have two curves, so C1 and C2. And if those two curves have the same boundary, in other words, they start at the same point and they end at the same point, right? So they have to have the same boundary. Very, very important rule. Right? Well, that means for a path-independent vector field that the green line integral and the blue line integral are equal. And so so this is what path independence means. Path independence means that these will always be equal in this case. Okay, old news, right? We've seen this before. Reminder, you can restate this as all closed line integrals have to be zero. What I'm going to do now is I'm going to take this, what we've got on the page, I'm going to rip it off shamelessly and just apply it one dimension up. Instead of looking at curves with boundary points, I'm going to look at surfaces that share a boundary curve. So kind of like what I'm doing with my hands here, right? This is a surface, this is a surface. The boundary of my right hand and the boundary of my left hand, look, I'm holding something in there that can't get out. It can't get out because, because those boundaries are the same. Right. And then I'm going to define the corresponding concept of surface independence. Again, it's a total ripoff. So here's the picture. Try to keep this all visible at the same time. If you have two surfaces, here's a surface S1. Here's a surface S2. Drawn, you'll notice here, so that they have the same boundary curve. And here's that boundary curve kind of going around like that. So that's the where my hands meet there, right? Okay. Imagine if, whenever this scenario happens, if two surfaces have the same boundary curve, it would follow in every such case. Wouldn't it be nice? And again, imagine, it's almost too much to ask, but what if every case of that, the fluxes through these surfaces were always equal? Outrageous to suggest that this would be true. Just like it was outrageous to suggest this, that how could you're telling me there's a vector field that doesn't care which path you integrate along? Come on. Right? Well, it turns out, of course, yeah, absolutely, it works in a large number of cases. It's all gradients, right? Well, there is this corresponding notion of surface independence. That in certain circumstances, there are certain vector fields which, when the boundary curve is shared, the fluxes are always equal. It doesn't matter which surface you pick. The flux is independent of the surface independence. Natural, very natural choice of words there. Okay. All right. So again, now notice the color pattern. Oh, and in fact, the color pattern reminds me, I forgot to give you the rephrase, an alternative version of this. Notice, you got to think about the orientations. Oh, let's see here. I guess I'd better zoom back in so I can talk about these orientations. In order for these two surfaces to have the same boundary curve, these two orientations, you got to make sure you do it the right way. You can't sort of get it wrong. The orientation matters. And in fact, in order for this to work, in order for your boundary to be oriented, and let's say I'm going to have it be oriented the way I've got it drawn here, right? Then you need the green orientation to be outward, and you need the blue orientation to be inward. Now, that seems counterintuitive, right? But let me just bring you back over to here. It seemed a little counterintuitive, really, when I said that these two curves have the same orientation in some sense, right? Well, in the sense that they have the same boundary points, but doesn't it seem wrong? This one's going counterclockwise. This one's going clockwise. Aren't those different? Well, depends on how you look at it, I suppose. They're different as how they are part of the boundary of the solid in between, sure. But they're the same in terms of what their boundaries are, right? So same deal over here. If you want to think about inward and outward, then yeah, as part of the boundary of this solid R, one of them is inward and one of them is outward. Those seem kind of different. But in terms of what their boundaries are, a better way to think about it is both of these orientations, they're both what you might call upward. Right? Okay. So you gotta think carefully about those orientations anyway, with that in mind. In the same sense that that these two line integrals being equal is the same as saying that there's a closed line integral that's 0. Likewise here, these two fluxes being equal is the same as saying that the corresponding closed boundary flux is 0. And corresponding meaning the surface like this that is oriented this way. So 2 different points of view on surface independence. Now, again, I'm a big believer, y'all know, big believer in the analogy. So I want you to take some time and think through everything we've said about surface independence. It's just highly analogous to what we've already said about path independence. What we don't yet know is, are there any surface independent vector fields? We know there's path independent vector fields, and let me remind you how we know. The reason we know there are path independent vector fields, I want to get back here. Oh, come on, erase the, oh, come on. Is because of, where is it? Here it is. This argument. Every gradient, fundamental theorem of line integrals tells me every gradient I can evaluate line integrals by just looking at the boundary. So every gradient is path independent. Really easy argument. Thank you, fundamental theorem of line integrals. So here's the analogous argument here for surface independence. Stokes' theorem does it for us instead. And specifically, it's if you have a curl field. If you have a curl field, Stokes' theorem says you can evaluate fluxes of curls by looking at the boundary. In this case, the shared boundary, they both have the same boundary. And so you get the same boundary line integral, and therefore these two fluxes are always the same. Whenever your green vector field is a curl, Stokes' theorem lets you draw this conclusion that they are also surface independent. Lot to digest. I know it's easy to choke on all the ideas. I'm cramming down your throats all at once here, right? So take the time, use the recordings to listen to 30 seconds of this, pause it. Wait, what, how did that work again? Think it through, right? And then start the recording again when you feel comfortable with it. There's a lot going on. Let me pause for questions. Yeah. G is the I guess you'd call it the anti-curl. It's the whatever, I'm claiming F is a curl of something. So G is just whatever that thing is that it's the curl of. Yeah, right. Okay, so every gradient is path independent. Every curl is surface independent. Okay. Now there's another local test. And this is highly analogous. Again, you're going to notice already from the way I have it laid out on the page. Let's see, just for comparison purposes, I want to have this up at the same time. Here's the Green's theorem version of it. This is our first version that we saw of this kind of an argument. And ultimately, it was path independence and these statements about Green's operator that were connected by way of Green's theorem. Okay, so what we've got over here, it's highly analogous as it turns out, but different. So here we have three statements about surface independence that we've just talked about. Being a curl is the same as being surface independent, which is the same as closed fluxes being zero. So again, it's not, none of those are the same statements as we have here, but they're highly analogous. And then here's some statements about divergence that I think are pretty believable. Divergence is zero, is the same statement as all possible triple integrals of divergence are all zero. And again, just ask yourself, what integrand could possibly have the feature that no matter what the domain is, every possible domain, the triple integral is always zero? That integrand possibly be? And I claim zero is the only such thing. Okay, so the connection between these two ideas, Gauss's theorem, because it connects fluxes to triple integrals. Right? Closed fluxes are triple integrals of divergence. So the analogy, crazy strong. Right? Green's theorem connects ideas about gradients to ideas about Green's operator. Gauss's theorem is connecting ideas about curl to ideas about divergence. And so this is another local test. If you find yourself looking at a vector field and you're like, hey, I've got a vector field. Is it a curl of something? Is there an anti-curl? Or more likely to be relevant, I've got a vector field. Is that vector field surface independent? Reasonable thing to want to ask, right? Wouldn't it be nice to be able to take your surface and just change it however you like? Keeping the boundary fixed, of course, but wouldn't that be awesome? How do I tell if my vector field is surface independent? Answer, no problem. Take divergence, compute the divergence. If you get zero, you're good. And here's an example. Oh, I'm out of time. Okay, well, we'll do the example next time. Sorry about that. Anyway, yeah, good stopping point. Oh, yeah, so some of y'all came in late because of buses, apparently, no problem. We'll do attendance in just a second here. And also, let me just, while everybody's still here, want to make sure everybody got the email. If you want to come to the outside lecture I'm going to be teaching on Friday, you are welcome. Feel free to come. Attendance will count just fine. So you can not come in the morning and come in the afternoon instead. Again, this is a one-time offer just for the outside class because I just want to be fair, you know, to everybody, even though I couldn't do it for our class. Okay. So yeah, let's do attendance. Oh, let's stop the recording here. Sorry, silly me. I can get this to okay, stop and see y'all later.